Okay, sounds good. Looks like a small crowd. I think I may have forgotten to post a title in abstract, which could be part of it. Oh, okay. Oh, they can do that? Oh, I see. Oh, I see. That's all right.
Recording in progress.
All right. Thank you so much. It's nice to be here virtually. Oh, there's a little bit of an echo, so please let me know if there's any issues with the audio. And since it's kind of an intimate crowd in person, please feel free to ask me questions if you have any. I think you might need to use the microphone that Koji has. So, but yes, please just interrupt me. Okay, so I want to talk a little bit about some kind of basic questions about solutions to algebraic differential equations. So let me introduce those questions. So here's I think a question that goes back to maybe the very beginning of like what the very first questions people asked about differential equations, which is given a differential equation, can you explicitly write down solutions? So what does explicitly mean? I think the traditional way of formulating this question is you come up with some collection of allowed functions, like what you call classical functions, and then you want to know, can you write down a solution to your differential equation in terms of those classical functions? So I think maybe traditionally people would allow things like, addition and multiplication, square roots and sines and cosines and that kind of thing, exponential functions. But for this talk, I want to focus on just algebraic functions. So I'll describe what that means formally in a second. But let me just remark, I think in this form, the question goes back to Fuchs in 1875, who asks the question, how do you recognize, given a differential equation, if the solutions are algebraic? And here, let me just say precisely what I mean by a function being algebraic. I mean that there's a polynomial that is satisfied. So there's a polynomial, say, with complex coefficients, p, so that p of f of z is okay. So that includes things like taking square roots and cube roots, but also some kind of more complicated functions, like the taking the solution to a degree 5 polynomial with indeterminate coefficients, which I guess all of you know you cannot write in terms of radicals. So it's a slightly more complicated set of functions. Okay, and this question actually, in some form, goes back before Fuchs asked it in general. So in 1873, Schwartz classified all the A, B, and C. So this particular differential equation has algebraic solutions. Okay, what is this differential equation really? So this is a form you can put any differential equation with regular singularities at 0, 1, and infinity into. So this is the so-called hypergeometric differential equation. And Schwartz wrote down all the parameters, A, B, and C here, so that the solutions to this equation are algebraic functions. And there's some small list now called Schwartz's list of such parameters. Okay. Are there any questions about this so far? Okay, so let me give you an example just to show you that even in the simplest cases, the answer can be a little bit subtle. So here's a differential equation. So here, A is a complex number, and the equation is d dz minus a over z times f of z equals 0. So this is a linear differential equation, and it's pretty easy to write down a full set of solutions. The solutions all have the form a constant times z to the a. Okay. And I mean, so when is this an algebraic function? Well, the answer is pretty easy to tell. Well, it's clearly algebraic if a is a rational number, because then you're taking a root of z and raising it to some power. And it turns out this is the only way these functions can be algebraic. It's not too hard to see. In fact, it's the only way they can be finitely branching. Okay, but I think this should immediately tell you that this is kind of a hard problem. So this says that this answer to what looks like kind of an algebra analytic question, like when is a solution to a differential equation have some special form, it turns out that it has some arithmetic hidden in it. So the answer says, well, A is a rational number, right? And that's sort of an arithmetic condition. Okay. So at least for linear ODE, this question, like when does a differential equation have algebraic solutions, has kind of there's kind of a traditional conjectural answer to it. And so I want to briefly discuss that before going into sort of more general situations. So this is the growth in Katz's p curvature conjecture. And here's a sort of baby form of it, which will be enough for this talk. And in fact, it's equivalent to what people usually write down in terms of somewhat fancier language. So one starts with a linear ODE. So what does that look like? It looks like d dz minus a times f of z is 0. So here, f is a vector of R holomorphic functions. And A, I want this to be an algebraic differential equation, so I'm going to say A is an R by R matrix of rational functions. And we want to know, when does this have a basis of algebraic solutions? Or equivalently, when are all the solutions to this ODE algebraic? And the conjecture is some kind of arithmetic condition. Namely, you take this operator d dz minus a, you raise it to the pth power, and you ask, as a differential operator, like on the ring of polynomials, is it 0 mod p for almost all primes p? Okay, so let me give you an example of this. So let's look at our previous differential equation. So that was the operator d dz minus a over z times f is 0. So let's see what happens when we raise this to the pth power and reduce it mod p. And you can just do a little computation. So you get, when you apply it to the monomial z to the n, you get n minus a times n minus a minus 1, all the way up to n minus a minus p plus 1 times z to the n minus p. Okay, so the Grothendieck-Katz p curvature conjecture predicts that a is a rational number if and only if this product here is 0 mod p for almost all p. Okay, and it's a little exercise that that's true. So in this case, it amounts to the Chebyshев density theorem for the field extension Q of A over Q. At least if A is an algebraic number, and then one can make sense of things in the transcendental case, but maybe I won't do it in this talk. Okay, so already you can see that to prove the Grothendieck-Katz p curvature conjecture for like the simplest possible differential equation you can write down requires some, I think, reasonably deep mathematics. The Chebyshев density theorem is not a totally trivial statement. And in fact, this conjecture it's really a conjecture. So there's very few cases that are known. Let me briefly summarize a few of them. So what are the known cases? What is the evidence for this conjecture? So Andre Bost and Chudnovsky showed that it's true for first order ODEs. That includes the case I discussed, the example I just discussed. And more generally, they prove it for ODE with virtually solvable monodromy. I guess looking at who's in the audience, probably you all know what that means, but at least one case that covers is the case where that matrix A in the differential equation d dz minus a times f of z is 0 is upper triangular. And so it covers a bit more than that. Okay, I think the most significant evidence in favor of the p curvature conjecture is the fact that Katz proved it for Picard-Fuchs equations. So since that notion will show up again later in the talk, let me briefly describe what this means. So I think the simplest way to say it is these are the ordinary differential equations satisfied by integrals of algebraic differential forms. So here, f of lambda is a function, and it's constructed as follows. You take a family of differential forms, omega lambda, so these depend on lambda, and you integrate them along a cycle. And so here, you should imagine you have some family of algebraic varieties. Let me be a bit more precise here. So we have a family of algebraic varieties x to s. You have a family of differential forms on the fibers, and then you take a family of cycles and you integrate along them. So to be really precise, what you do here is you have a smooth proper morphism. You take the flat bundle whose fiber is given by the cohomology of the fibers of your morphism, and this carries a flat connection. And so in particular, if your base is an open subset of the complex plane, a flat connection on a vector bundle is just the same as the ordinary differential equation. And so Picard-Fuchs equations are the ordinary differential equations that arise that way. And I'll give you some examples of those later in the talk. They're really concrete things you can write down. Okay, and maybe let me just remark, I mean, there's a lot of interesting, very recent ongoing work, or sorry, very recent work about the B-curvature conjectures. In particular, Eno Groening verified it for rigid Z local systems. You know what that means? Maybe let me remark that if you believe standard conjectures, rigid Z local systems are examples of Picard-Fuchs equations, but we don't know those conjectures. So it's at least in principle a very recent and new evidence for the P-curvature conjecture. All right. Are there any questions so far? Okay, so I mean, at the beginning of the talk, I said we want to understand something about algebraic solutions to differential equations, and I didn't say linear differential equations. Okay, so what about nonlinear differential equations? And let me just give you like an example of a nonlinear ODE whose algebraic solutions you might be interested in. So this is the Penn-Levy-6 equation. It's a nonlinear ODE because of this dy dt squared term here. And I guess there's also, it's very nonlinear in y in a number of places. So there's 4 parameters here, alpha, beta, gamma, and delta, and you fix those, and then you solve for y as a function of t. And maybe let me just remark that algebraic solutions to this particular ODE have been studied for, well, I guess since it was written down in 1905, and they were classified eventually by Lissovi and Tichy in 2014. So it took about 110 years. And it's a really a kind of involved classification. So just to briefly summarize what the classification looks like, there's 4 continuous families of algebraic solutions, 1 countably infinite discrete family, and 45 exceptional algebraic solutions for various parameters. The Lissovi-Tichy's classification was computer aided, and I think we still don't have kind of a conceptual of complete conceptual classification or proof that the classification is correct. And yeah, go ahead. Oh, I will tell you where it comes from in a little bit. It's but Martin, maybe let me just say that it's the first example of a non-abelian Gauss-Manin connection. So I don't know if that answers your question, but that's what I'm going to explain in more or less the second half of the talk. So all I want you to get from this so far is this is some famous ODE that at least some people care about. Like they worked, you know, a bunch of Hitchin and Bolch and a bunch of other people worked pretty hard to classify the algebraic solutions, and eventually that work was actually great. But let me just draw your attention to some kind of weird feature of this maybe weird feature of this ODE if you're used to linear ODE, which is like if you have a linear ODE, basically if it's irreducible, either all the solutions are algebraic or none of them are algebraic. So maybe another way of saying that is like in the space of solutions, there's some sub-vector space of algebraic solutions. But for nonlinear ODE, like you can have some, depending on your initial conditions, you can have just really some sporadic algebraic solutions. So the sort of the structure of the algebraic solutions of a nonlinear ODE is a lot more complicated than the structure of for a linear ODE. And in particular, like the P curvature conjecture, it's sort of you can't expect I think such a clean conjectural description of the algebraic solutions because that's a conjecture about when all of the solutions are algebraic. And here you just expect there to be some random kind of sporadic ones. Okay. Okay, so let me make a conjecture. So as far as I know, this conjecture is new, but I'll talk a little bit about you know some of the precursors, and then I'll try to give you some evidence for it. Okay, so suppose I have a nonlinear ODE. So let me say precisely what I mean by that. So here's some nonlinear ODE. It's an expression for the nth derivative of f in terms of z, f of z, f prime of z, all the way up to fn minus 1 of z. So this is like a slightly special form of a nonlinear ODE. So in particular, this f of n is isolated. So sometimes people call these things quasi-linear. this condition just guarantees that that one can write down a formal solution to the ODE. And here f is going to be a rational function in n plus one variables, capital F. If this is not general enough for you, you can think arbitrary horizontal foliation, and I would make the conjecture in that generality too, but let's just stick with this sort of more elementary setup. So I want this to be an ODE, and I want to take the Taylor series expansion of a solution at a non-singular point of this rational function, capital F. So here, these are the initial conditions, and the way I've set things up, there's always a power series expansion of the solution. And the conjecture is that f of z is algebraic if and only if there's some integer, a positive integer, I guess, so that all the coefficients of the Taylor expansion of f lie in z adjoin that 1 over that integer. Okay, so, and if you don't want to work over q, the conjecture is that all the coefficients of the Taylor expansion lie in a fixed finitely generated field. Okay, so that's the conjecture. One direction is really easy. So the forward direction, that an algebraic function has this property that all of its Taylor coefficients lie in a particular finitely generated Z algebra, is a theorem of Eisenstein from 1852. Okay, so maybe let me just show you some examples of functions to show that this is like a reasonable conjecture. So if you look at the function e to the x, this is sum of x to the n over n factorial, and here you see n factorial has infinitely many primes showing up by a theorem of Euclid, I guess. So maybe here's an algebraic function. You can take 1 plus z to the 1/2, so the square root of 1 plus z. What's the Taylor expansion of this? It's like 1/2, sorry, 1/2 choose n times z to the n, sorry. And it's a little exercise that 1/2 choose n is a unit away from 2. So it only powers of 2 appear in the denominator. So this is an algebraic function, and you see, at least in this case, Eisenstein's theorem is true, that it's only finitely many primes in the denominators of these Taylor expansions. And okay, let me just do one more example. So minus log of 1 minus z is sum of z to the n over n. So again, infinitely many primes show up in the denominator. Hopefully I did that right. And log is not an algebraic function. So that's some another piece of another example. It's true. Maybe let me just observe that there's like a pretty big difference between this log here and this e to the x, which is like these n factorial has a lot of denominators, and n is not p-adically 1 over n is not p-adically very large. I guess depending on how you quantify these things. And this is sort of a general feature of functions coming from algebraic geometry. So log is a period, and it's known that these sorts of period integrals give you g functions, which are that's a theorem of like Dwork and Andre, I guess. The power series expansions of these functions coming from algebraic geometry, the denominators don't grow too quickly. So in some sense, maybe they're not that far from algebraic functions. But that's just an aside. That's not really relevant at this time. Okay, so maybe let me make some remarks about this conjecture. So I think for linear ODE, this conjecture has appeared in the literature. So I've seen it attributed to Andre and Cristol, although I think that the history maybe goes back a bit further. For linear ODE, there's some things that kind of look like counterexamples. So they're not, and it's because I specified that one has to expand around a non-singular point of this ODE. So for linear ODE, sometimes there are solutions at a singular point, so not a full basis of solution, but some sort of lower dimensional space of solutions. And those solutions can have this property that their Taylor series expansions are integral. So here I've written down an example. So if you take f of z to be 5n factorial over n factorial to the 5th times z to the 5th, this power series satisfies a linear ODE. And you can do a little computation, like you can do the p-adic valuations of these numbers and check that they're integers. But this is not an algebraic function. Okay, but I claim this does not contradict the conjecture because it's a power series expansion of a solution at a singular. I don't know of a counterexample for linear ODE, and I'll talk a little bit about what we do know for linear ODE shortly. Okay, you can ask, I think very reasonably, what's the relationship to the p-curvature conjecture that I discussed before? And I think there's no direct relationship. As far as I can tell, it doesn't imply or follow from the p-curvature conjecture. but it's not so hard to write down a slight strengthening of this conjecture, basically where you only ask that certain coefficients don't have powers of p appearing in the denominator, which does imply the p curvature conjecture. And every result, I'll say, on the conjecture I just told you about actually holds for the stronger conjecture. So you can ask me about it at the end of the talk if you'd like. Okay, so two more remarks. So first of all, there's a related conjecture by Heckedal, Shepard, Barron, and Taylor, which tries to, in the spirit of the p curvature conjecture, which tries to characterize when all solutions to a nonlinear ODE are algebraic. And I think that conjecture is really interesting. It's completely open, but I think it's somehow not as strong as you would want, just because, like, typically for a nonlinear ODE, there's some sporadic algebraic solutions and some and then the sort of general solution is not algebraic or can be kind of wildly transcendental. And then maybe let me just remark, I think the first case where something like this conjecture shows up is, so I told you there was this work of Schwartz uh, classifying the hypergeometric ODE with algebraic solutions. And Landau gave a different proof of that Schwartz's list was correct, more or less in terms of this conjecture. So he studied the hypergeometric functions that have this integrality property, and then showed the only ones that had it were the ones appearing on Schwartz's list. So at least for these sort of basic hypergeometric functions, the conjecture seems to be true for expansions at certain points. I'll come back to that. And maybe let me just remark, I mean, so I discussed this close counterexample here. So near counterexample here. So Kristol does have a conjecture which characterizes, at least conjecturally, when a power series expansion of a solution to ODE at a singular point should have integrality property. But that won't be relevant for the rest of this talk. I just want to mention it exists. All right. So that's the conjecture. Let me kind of go back to the conjecture and just show it to you so you can absorb it, and then I'll tell you what we were able to prove. And so maybe now is a good time to pause and see if there are any questions. All right. Oh, Koji, did you have a question? No. So you can, so any f will have coefficients in some finitely generated Z algebra because it's a rational function, and then the conjecture just becomes that that the Taylor expansion of f has coefficients in a finitely generated Z algebra. So that's the I tried to make it as elementary as possible. But yeah, the conjecture. Yeah. Sure, yeah. So in fact, everything I'm gonna say, well, okay, the conjecture is for arbitrary horizontal foliations. So in other words, you have x to s, you have a horizontal foliation on x over s, and then the conjecture should be that a leaf of the foliation is algebraic, if and only if it has some integrality property. So if the leaf descends to some finitely generated Z algebra. Does that answer your question? Yeah. So that's the generality I would make the conjecture, and all the theorems I'm going to state are true in that generality. Again, I just wanted to again keep things elementary. Any other questions? Okay, so let me tell you some results. Okay, so I'm going to tell you a result about nonlinear ODE, but I just first want to tell you some things we can prove for linear ODE. And then we'll come to at least a result for nonlinear ODE, including that Panlevet-6 equation I mentioned earlier. Okay, so let me describe the class of linear ODE I'm going to study. So it's more or less the same class studied by Katz, so Picard-Fuchs equations. So let me just remind you what those are. So here, x to s is a smooth proper morphism. I've written S as a subset of A1 because that way you get an ODE, but that's not important for anything I'm going to say. So in fact, what I'm going to say is true for arbitrary S. So since there's a bunch of experts in the audience, maybe let me cross that out. And so one gets a linear ODE whose solutions near a point Z0 in S so whose local solutions are in bijection with the cohomology of the fiber of this morphism pi at Z0. Okay, so what's really happening here? So you take the flat bundle whose fiber is the cohomology of the fibers of pi, so that's Ri pi lower star C tensor O, that has a connection on it which measures how much a section is failing to be locally constant. So the fibers of this morphism, being a smooth proper morphism, are all homotopy equivalent to one another. So if you have a cohomology class on one, it sort of canonically deforms to the nearby fibers. And this connection measures that the flat sections to this bundle are precisely those canonical deformations. So these are called Picard-Fuchs equations, or if you allow S to be an arbitrary base, they're called the Gauss-Manin connection. Okay, so the first theorem is it's true. The conjecture is true for these ODE with an assumption on the initial conditions. So if the initial conditions here in the initial conditions are a homology class in the fiber, it's true if that's the class of an algebraic cycle. So this is, I guess, some form of Katz's theorem so it's some analogous to his theorem on the p-curvature conjecture. So we do not know in particular, we don't know this conjecture for general initial conditions, and I think that shouldn't really surprise you. So the hypothesis of the p-curvature conjecture is something about every solution to the ODE. So namely that this connection or the differential operator you have has it's identically zero, powers of it are identically zero mod p. Here we only have information about one solution to the ODE, and so the theorem says we're able to check this conjecture. So if you have a solution to this ODE whose initial condition is the class of an algebraic cycle, and it has this property that the Taylor series coefficients only have finitely many primes showing up in the denominators, then that's an algebraic function. Okay, so that's the first result. So the second result is that the conjecture is true if your power series f of z satisfies a second order ODE of geometric origin. So what that means is a second order ODE which shows up as a summand of one of these. Okay. And then maybe a corollary is that if you believe some standard conjectures, so in particular the Bombieri-Dwork conjecture, it doesn't really matter what that is, then the corollary is that the conjecture is true for all second order ODE. And of course, this conjecture is very open, but I think it's sort of commonly believed. So at least there's some evidence a strong evidence, I think, that this conjecture is true up to order 2. All right, are there any questions about this so far? Oh, sure. So the Bombieri-Dwork conjecture says that if you have a holomorphic function which satisfies a linear ODE, and it's the coefficients of its power series expansion have denominators which don't grow too quickly, so it's called a G function, then the minimal ODE it satisfies is of geometric origin. So of course, if you have this integrality property, the coefficients of the Taylor series expansion of your power series, the denominators grow very, very slowly. And so in particular, the Bombieri-Dwork conjecture implies you're in the situation of being of geometric origin. Yeah. Great. Any other questions? Okay. So let me give you an example. So here's a second order ODE of geometric origin. It's the Picard-Fuchs equation, meaning it comes from the universal family of elliptic curves. And well, I told you that the conjecture is true for ODE of geometric origin. So in particular, it's true of second order ODE of geometric origin. So in particular, it's true for this one, for arbitrary initial conditions. I think I would say I don't think this theorem is rocket science for this particular ODE, but I don't think it's so obvious. I mean, you really need the fact that it's true for arbitrary initial conditions. It's actually some arithmetic. It requires some arithmetic of elliptic curves. It's not, and this sort of statement about second order ODE really requires some arithmetic of abelian varieties. It's really not there's some number theory going into it. All right. Are there any other questions? Yeah, so I mean that the corresponding flat bundle is a summand of something of this form. So the corresponding flat bundle is some rank 2 flat bundle, and I would like it to be a summand of a Gauss-Manin connection. Yeah. So a second order ODE is a linear ODE where the second derivative of f appears. Oh, I see what you're saying. Yeah, so right. So maybe the way I described a linear ODE before, you have like ddz minus a times f is zero, and that's a first order ODE. But if you have any second order ODE, you can always convert it into a first order ODE where A is now a 2 by 2 matrix. So there's this companion matrix construction that lets you exchange the rank of an ODE with its order. I don't know if that answers your question. So somehow a second order ODE is the same as a two-dimensional flat bundle, well, with a cyclic vector. Does that answer your question? Yeah, sorry. I should say one kind of really fun thing about this project is that I've learned a lot about ODE over the course of doing it. And somehow, I'm an algebraic geometer, and I don't think I ever took an ODE course in undergrad or whatever. But now I'm really enjoying it. Um, okay. Any other questions before I move on? Okay. So let me tell you what we know how to prove for nonlinear ODE. Okay. So if you are sufficiently philosophical, you should think of what I'm going to tell you as some kind of non-abelian analog of what I called theorem A about cycle class initial conditions. So let me tell you the statement, and then the rest of the talk will be devoted to unwinding what it means and maybe why you should care about it. Okay, so the theorem C, and by the way, just like everything else in this talk, it's joint work with Josh Lamb, is that the conjecture is true for isomonodromy ODE and Picard-Fuchs initial conditions. Okay, so I'm going to explain. I put these things in quotes because they need explanation. But you should think that, well, I told you there was some theorem which is true for Gauss-Monod connections or Picard-Fuchs equations at cycle class initial conditions. And here you should think of isomonodromy as the non-abelian analog of a Gauss-Monod connection, and Picard-Fuchs as an initial conditions as the non-abelian analog of being a cycle class. Okay, so the rest of this talk will be devoted to explaining what this theorem means and why you should care about it. But maybe before I continue, let me just remark that as far as I know, this is like the only known case of that conjecture, but also of like any kind of general algebricity result for nonlinear ODE. Okay, so maybe it's premature, but before I start explaining what these words mean, are there any questions about the statement of the theorem? Okay, great. So let me first of all just give you some examples of isomonodromy ODE. So I think the first example from 1905, which was written down by Richard Fuchs, not by Penlevet, is the Penlevet-6 equation, which we saw earlier. So it's this kind of complicated expression. And then let me give you kind of a more complicated nonlinear ODE, which is also I like a bit more, which is an example of one of these isomonodromy ODEs. So this is the Schlesinger system, which was written by Schlesinger in 1912. And he more or less had this, what I'm going to describe to you, in mind. So this sort of subject of isomonodromy has an old history. So you have n matrix valued functions of n points in CP1. So B1 through Bn, they have the property that they sum to zero. And then what's your ODE? So you can take so these are functions, the BI are functions of lambda 1 through lambda n. And so you can take the derivative of BI with respect to lambda j. And if I is not equal to j, the derivative is this expression. So you take the commutator of BI and BJ and divide by lambda I minus lambda j. So that's what you do if I is not equal to j. So now I have to tell you how you take the derivative of BI with respect to lambda I. And well, what you want to do is you want to make sure that this expression stays true. So you want the sum with respect to I of dBi over d lambda j to be zero. So for all but the I equals j term, you can plug in this expression here, and this tells you what dBi d lambda I is. Okay, so where does this come from? So let me tell you what this really means and why you should care about it. So what is isomonodromy? So again, just like before, you start with a smooth proper morphism of algebraic varieties, if you'd like over C, although it doesn't really, well, for now, let's be over C. Here again, I've written that S is a subset of A1, so you get a ordinary differential equation, but well, I've already given you an example, namely the Schlesinger system where S is general, and again, everything I'm going to say is true if S is general. And I want to give you from this a nonlinear ODE, And so let me tell you what its local solutions near a point z0 in S are in bijection with. So what are the initial conditions? So the initial conditions, before they were the cohomology of a fiber. Now what they are is the space of representations of pi1 of a fiber into GLRC. Okay, so let me briefly say, like, why does this give you a nonlinear ODE, or if you'd like, why does it give you some kind of foliation? Well, if you perturb Z0 a little bit, you get a different fiber of this map, which is has a different complex structure, but is homotopy equivalent to what you started with. Just because this is a smooth proper morphism, all the fibers are homotopy equivalent to each other. And so in particular, if you start with a representation of pi1 of a fiber and then start moving which fiber you're on, your representation comes with you for free. So that's exactly what you need to write down a foliation. So the leaves of this foliation are families of representations of pi1 of the fibers whose monodromy representation is, or where the corresponding representation is it has locally constant isomorphism class. So this is what isomonodromy means. So let me give you a couple of examples. So Penleve-6 is what you get if you take S to be the configuration space of 4 points in P1. So if you take the ordered configuration space, that's P1 minus 0, 1, and infinity. X is the universal family of P1s with 4 marked points. And you only look at representations which factor through SL2. Okay, so maybe let me make a quick remark here, which is that, strictly speaking, this doesn't fall into the formalism I've written here because I don't have a smooth proper morphism. I've taken a family whose fiber over a point of S is P1 minus 4 points. But okay, you can make sense of everything here if there's a relative normal crossing this compactification, and that's what we have, and I will not say anything more about that. Okay, and then what happens with the Schlesinger system? Well, you just do the same thing where S is now conf n of CP1, X is the universal family, and you look at R-dimensional representations of pi1. Okay, so let me describe a little bit the monodromy of this ODE. So if you have a ODE of the form I've been describing, there's a sort of representation associated to it. So for a linear ODE, what do? You take a basis of solutions to the ODE, you analytically continue them in a loop, and you get a new basis of solutions. So in other words, loops act on the space of initial conditions. So pi1 of the base acts on the space of initial conditions for your ODE. And that's the monodromy representation of a linear ODE. Well, for a nonlinear ODE, well, at least in this case, what do you get? There's a similar story. So I have this map X to S, which is smooth and proper. And just because you have a long Z sequence in homotopy groups, pi1 of S has an outer action on pi1 of a fiber. So if you have a loop in a fiber, you can drag it in a circle around a loop in a base, and you get a new loop, which is well-defined up to conjugacy. Because there's some base point issue. So that's what it means to give an outer action of a group on another group. And that action descends to an action of pi1 of S on the space of conjugacy classes of representations of pi1 of the fiber. Okay, so let me just tell you in this language what algebraic solutions to this isomonodromy ODE are. So an algebraic solution to this isomonodromy ODE is a finite orbit of this action I've just described, of pi1 of the base on representations of pi1 of the fiber. Okay, so let me just give you a warning, and then I'll sort of explain briefly how to address the warning. So the description I've given you of this isomonodromy ODE is completely analytic. So in particular, I used like pi1 everywhere, and like GLNC and stuff like that. And so I'm not using atal pi1 or anything. I'm really using the topological pi1. But to formulate the conjecture, it's really crucial that the ODE one studies are algebraic, right? Like they have to live over a finitely generated Z algebra, and then one can start looking at the Taylor series expansions of the solution. So let me just briefly be a bit more precise about what this ODE looks like. So here we have some smooth proper morphism. To it, we associate what's called the de Rham moduli stack. So M de Rham of X over S, this lives over S. And loosely speaking, its points are flat bundles on the fibers of pi. So a C point of this, at least, is a fiber. So a point of S, which you can think of as a fiber of this map XS, and then a flat bundle E nabla on the fiber. And well, this properly speaking, this is a stack, so maybe ignore this modulo isomorphism. And this carries a horizontal foliation, so more properly, it's a crystalline stack. So for S, and let me just describe analytically the leaves of this foliation. So they're families of flat bundles on the fibers whose monodromy representations have locally constant isomorphism class. Okay, again, that it's not obvious that that foliation is algebraic, but at least I've uniquely described one foliation, or one crystal structure of C. Um, and in fact, it's true that foliation is algebraic. True, but not obvious. So it's uh, I would say maybe a bit easier than the fact that the Gauss-Monod connection is algebraic, but I don't think it should be totally obvious to you. But nonetheless, it's true. This is an algebraic foliation or an algebraic ODE. And in the examples I wrote down earlier, it's sort of obviously algebraic. And I literally wrote down as an algebraic nonlinear ODE. By the way, it's really, if you get bored during the rest of the talk, it's a really fun exercise to prove that, or to derive the ODE I wrote down from this description. Okay, are there any questions about what these isomonodromy ODE are? Okay, so I think you should think of them as some kind of non-abelian version of the Gauss-Monod connection, and I think Simpson actually calls them that. Like what they the Gauss-Monod connection measures how the cohomology of a variety is moving around as you change the complex structure, and this is measuring how representations of the fundamental group move around as one varies the complex structure. Okay, so let me recall the theorem was, so that it was that this conjecture that a solution to this ODE is algebraic if and only if its Taylor series expansion has coefficients lying in Z adjoining 1 over n, or maybe more generally, finitely generated Z algebra. It's true for these isomonodromy ODE at Picard-Fuchs initial conditions. So I've now hopefully explained to you what isomonodromy ODE are. So now let me explain what a Picard-Fuchs initial condition is. And you've actually seen it already. So let me recall the setup. So we have some smooth proper X to S, and I gave you some ODE whose initial conditions are in bijection with the space of isomorphism classes of representations of pi1 of the fiber. So an initial condition is a representation of pi1 of the fiber, or if you'd like a flat bundle on the fiber. And I'm going to say that's Picard-Fuchs if there exists some smooth proper morphism y to the fiber of this map, so y to x0, such that rho is the monodromy of the cohomology of F. So this is more or less what I told you was a representation of geometric origin before. So except that I really want it to be the whole cohomology of the fiber. So another way of saying this is that this rho is Picard-Fuchs if it shows up as the action of pi1 of the fiber on the cohomology of the fiber of some other morphism. Okay, so it's a little bit of a complicated statement, but let me just like briefly say, like, a huge amount of algebraic geometry is devoted to understanding which representations have this property. So if you want to understand, like, this is the problem of classifying local systems of geometric origin, and I think it's somehow the best approximation we have to trying to understand, like, what is the topology of an algebraic map. It's which representations show up in the cohomology of a family of algebraic varieties. Okay. Are there any questions about this? Okay, so what we've done is we've proven this conjecture is true for this class of ODE at... Oh yeah, go ahead. Yeah, that's right. So more generally, yeah. So here you can let X and S be arbitrary. It doesn't have to be inside of A1. And here, yeah, the condition is saying that it's a Gauss-Monod connection. That's right. So the reason I call it a Picard-Fuchs initial condition rather than saying a Gauss-Monod connection is that there's some disagreement in the literature about whether a Gauss-Monod connection is a summand of a Picard-Fuchs equation as I've written it, or the whole thing. And I really need it. I need a Z structure, so I really need it to be the whole cohomology. So that's the reason for the terminology. Are there any other questions about this statement? Okay, so for example, for the Penlove-6 equation, there's some countable collection of initial conditions where we've proven the conjecture is true. I think you should think of this Picard-Fuchs initial condition as some analog of being a cycle class. It's like being a non-abelian cycle class. Okay, so let me briefly describe the known cases of the conjecture and then give you some more idea of maybe why I think you should care about this particular isomonodromy case. And I'll try to say a little bit about what goes into proving this kind of statement. Okay, so what's known? So you can deduce the case of the conjecture for degree 1 linear ODE with arbitrary initial conditions from Bosch's work on foliations. So this is not too difficult. For Picard-Fuchs equations, we know it if the initial conditions are cycle classes. So that was theorem A. For degree 2 ODE of geometric origin, we know it for arbitrary initial conditions. That was theorem B. And then for these nonlinear isomonodromy ODE, we know it for these Picard-Fuchs initial conditions, and that was theorem C. And I think this is actually a complete list of what's known about this conjecture. I would be very interested in hearing any more cases that are known. Okay. So in a minute, I'm going to try to give you some idea of really like why this is an algebraic geometry talk. So like what kind of algebraic geometry goes into studying this kind of statement. And then tell you a little bit more about why I think you should care about isomonodromy ODE in particular, even if you only really care about linear ODE. But before I do that, are there any questions? Okay, so let me say a little bit about what goes into proving this kind of statement. Okay, so let me just remind you what the conjecture says. So here we have some nonlinear ODE, and then the conjecture is that a solution to it is algebraic if its Taylor expansion about a non-singular point has coefficients lying in some finitely generated Z algebra. So the way I've set things up is lying in Z adjoint 1 over n. Okay, and I'm not going to say anything about the proof of theorem B. It's a little more technical, but theorem A says that this is true if your ODE is a Picard-Fuchs equation and your initial conditions are a cycle class. And theorem C says it's true if your ODE is an isomonodromy ODE and your initial conditions are Picard-Fuchs. Okay, so let me tell you what's special about these initial conditions. What extra structure is one using to prove this statement? So in both cases, we start with some smooth proper morphism. And then in theorem A, we have, well, what are the initial conditions? They're the cohomology class on the fiber. And in theorem C, you have a representation of pi1 of the fiber. And in the first case, I've assumed that cohomology class is a cycle class. And in the second case, I've assumed it's a Picard-Fuchs equation. So let me tell you what extra structure that gives you. So first of all, it gives you that C in the cycle class case. So a cycle class is famously in the ith cohomology of X intersected with it's an integral class in the ith piece of the Hodge filtration. And then also, well, there's a bit of extra structure too, which we use, but maybe I won't say anything about. In the case of so this was a Picard-Fuchs initial condition, meaning it showed up in the cohomology family of algebraic varieties. And the extra structure here is that it carries a Z variation of Hodge structure. So this is the cohomology of an algebraic variety carries a Hodge structure. And if you have a family of algebraic varieties, their cohomology carries a variation of Hodge structure. Okay. And the main idea of the proof is to show, well, we have this extra structure at the initial condition. The main idea is to show that under this arithmetic hypothesis on the coefficients of your Taylor series expansion, this extra structure extends over the universal cover of S. So in other words, if you have here you start with some function f, so that f of z0 is a cycle class, and you want to show that maybe not that f of z is a cycle class for all z, but that it stays in some given piece of the Hodge filtration. Or here, you have f of 0 corresponds to some representation, which is a Picard-Fuchs equation, and you want to show that f of z gives you a z VHS, a z variation of Hodge structure for all z. Okay, and doing this in theorem A relies on some properties of crystalline cohomology and the way that crystalline Frobenius interacts with the Hodge filtration. So more or less Mazur's theorem on the relationship between Frobenius and the Hodge filtration. And then theorem C is a bit more involved, so it relies on Sun-Yang-Zhuo's Higgs-Durand flow and August Vologodsky's non-abelian Hodge theory and positive characteristic. Okay, so let me just briefly say, given this extra ingredient that the integrality of this power series gives you some way of deforming the extra structure on one's initial conditions to the entirety of the base, how one wins. So in theorem A, you show that you have a class which lives in some piece of the Hodge filtration, In theorem B, you show that you have a ZVHS for all values of Z. Um, and well, what do you do? So in theorem A, the fact that you live in this piece of the Hodge filtration HII tells you that the pi1 orbit of your class is discrete. Well, it lives in integral cohomology, and compact because HII has a definite polarization on it. And then a discrete and compact set is finite. So what this tells you ultimately is that your function f, which is a solution to your ODE, actually has finite amount of branching. So this orbit is precisely the set of branches of your function. And then, okay, the fact that these ODEs have regular singularities tells you that having finite branching is the same as being algebraic. Okay, and then there's an analogous story in theorem B. So again, one wants to show one's function is finite branching. So let me just briefly tell you what the branches of this function are. So remember, we had a representation rho of pi1 of the fiber of our map. Pi1 of the base acts on that representation, or acts on the set of representations of pi1 of the fiber. And the branches of our function that we're trying to show are finite are exactly the orbit of rho under the action of pi1 of s. Well, what do we know? We know that this orbit consists of z variations of Hodge structure on our fiber x0, z0. And then Deline showed that an algebraic variety carries finitely many z variations of Hodge, or local systems underlying a z variation of Hodge structure of a given rank. So again, we get some. Yeah. Yeah. Sorry. Yeah. Yes. Both of these are theorem C. Sorry about that. Yeah. Okay. Yeah. Sorry. So again, the upshot again is that we get some finiteness coming from Deline's theorem on finiteness of local systems underlying a ZVHS. Okay. Are there any questions about this? Okay. So let me briefly discuss a couple corollaries of the proof, which I think are maybe interesting, and then say a word about why I think you should care about these particular nonlinear ODE. Okay. So the main corollary of the proof is just that, like, well, that you can sort of perturb these structures that come from a local system with geometric origin off the central fiber, if you can check this integrality hypothesis on some power series. Okay, and what's the main case where you can check this integrality hypothesis? Is where you already know that you have an algebraic solution to your ODE. Right. So in fact, the proof gives you some, I think, non-trivial input, even when the conclusion is trivial. So namely, so suppose you have a Picard-Fuchs initial condition to this isomonodromy ODE, and it gives you an algebraic solution. So in other words, if pi1 of s acting on this rho has finite orbit, um, then what you get is that all the isomonodromic deformations of this representation of this ODE carry a ZVHS. So this was already known, this theorem of Katsarkov and Pantev, but it's kind of a deep theorem. So this is a new and I think much more algebraic proof. You know that the P curvature of all the isomonodromic deformations is nilpotent, and in fact, the conjugate filtration deforms off the central fiber, or the conjugate filtration mod P, sorry, deforms off the central fiber in a canonical way. There's some F isocrystal structure and so on and so forth. And maybe if you're philosophically minded, you can think of these statements as some kind of non-abelian analogs of statements in the flavor of the variational Hodge conjecture. Okay. So let me just finish up by discussing a little bit the relationship to the classical P curvature conjecture. So let me describe, I think, a variant of the P curvature conjecture. So remember, the P curvature conjecture says you start with some ODE of the following shape. So ddz minus a times f of z is 0, where a is some matrix of rational functions. And you want to know when this is a basis of algebraic solutions. And the conjecture is that that's true. Also, the P curvature conjecture says that's true if ddz minus a to the p, so here I'm covering something up, is 0 mod p for almost all primes p. Okay, and you can ask for a stronger thing, which is also true if the solutions are algebraic. You can ask that ddz minus a to the p to the n is 0 mod p to the n factorial for almost all primes p and all integers n. Okay. And this is saying that this ODE underlies an arithmetic D module, if you know what that means. Okay, and the theorem, this is a joint work with Brian Lawrence. from a few years ago is that this conjecture I described before, just for isomonodromy ODE, so just for these non-abelian Gauss-Model connection, implies this variant of the p curvature conjecture for all linear ODE. Okay, so I think this is the main, and in fact, I expect some slight variant of this conjecture for isomonodromy ODE to imply the usual p curvature conjecture for all linear ODE, but that's work in progress. So maybe let me not claim anything. So I think that's one reason to care about these isomonodromy ODEs. So these things of geometric origin, but I think if you can really understand algebraic solutions to those, you can get access to the p curvature conjecture and related conjectures for arbitrary linear ODE. So at least for me, this is one reason to care about these isomonodromy ODEs. So I don't know if that answers Martin's question from the beginning of the talk, why you should care about Pan-Lebesgue and so on. Uh, but yeah, so I don't know if you should consider this work to be any kind of progress towards the p curvature conjecture, but I think at least it gives you some sort of interesting mathematics you can try to understand about nonlinear ODE and hope you're getting somewhere towards understanding more classical questions about linear ODE. All right, I think that's all I wanted to say. Are there any questions? So, sorry, I'm having a bit of trouble hearing you. Yeah, right. Yeah, so if you have a singular fiber, yeah, sorry. So if you have a singular fiber, you get a singularity in your ODE. Um, Yeah. Okay. I can say a little bit about this, right? So, okay. So if you have a singularity of your ODE, you usually can't write down a basis of solutions at all, of holomorphic solutions. But sometimes you can write down like a couple holomorphic solutions. So, for example, if the mono, like let's just say you're in the linear case, if the monodromy of your ODE about the singular point has invariance, then there's some local solutions at least. Um, and the conjecture is false if you expand if you take the Taylor expansion around such points. Um, so I mean that there's a reason I specified. Let me go back to the conjecture. So that there's a reason I specified that here these initial conditions are a non singular point of your ODE. Um, no, so there's a conjecture of crystal, which does try to characterize the solutions whose Taylor series expansions have this integrality property, and the conjecture is more or less that they're integrals of holomorphic differential forms on some family of varieties along a vanishing cycle. And the way Crystal says that is he says it's the diagonal of a rational function. And so maybe let me not define that, but Crystal's written a lot of really beautiful papers about this. So yeah, that said, I actually don't know. I don't know a good way of understanding, I mean, even conjecturally, when like a local solution expanded around a singular point is algebraic. I think that's a pretty good question. So you need some condition that's stronger than the Taylor expansions being integral, and it's not clear to me what that should be. I don't know if that answered your question, but at least that's some comment of what happens when you have a singular fiber. Sorry, say it again. Yeah. Of course. I mean, the conjecture is about the integral structure, but maybe let oh, go on. No, it's totally fine for. Sorry, when I say cycle class, I mean something in the image of the cycles tensor cube. It's you can kind of easily reduce to the case of an integral cycle because if n times a function is algebraic, then the function is algebraic. Yeah. So when I say cycle class, I mean a Q cycle class. Yeah, that's a good question. Sorry about that. Yeah. Yeah, there's a lot of integral structures in this work. So, all right, thank you guys for coming. It was nice to be there virtually, even briefly.
Recording stopped.
Yeah. Hi. I can't. Oh, hey, how's it going?